Okay, so in this video we're going to look at some of the calculations for rate of reactions and rate law. So for the first one, we want to look at how we can compare the rate of reactants to products. So if we have a balanced equation, 5a plus 2b goes to 7c plus d, if we know some information about either how fast a reactant is being used up or how fast a product is being made, we can relate that to something else in the equation or use it to determine the overall rate of the reaction. So if you remember from the previous video, the overall rate of the reaction is based on any component of the equation that has a coefficient of 1. So for example, D here has a coefficient of 1. So if we knew the rate information for D, that would be the same as the rate information for the overall equation. So in this case, we actually know information about C. The rate of formation of C is 0.15 moles per liter per second. We want to know the rate of the overall reaction. Alright, so if you remember, rate is equal to our negative 1/5 change in A over time equal to negative 1/2 change in B over time equal to 1/7 change in C over time, or equal to change in D over time. So remember, this equation comes from the idea where we have the reciprocal, or 1 over the coefficient, multiplied by the rates of each to set them equal to one another. So since I know the information for C, this number right here can be plugged in for this relationship. So then I can use it to compare to anything. So that means that my rate for the reaction is going to be equal to 1/7 of 0.15. Alright, so if we look at our calculator then, 0.15 divided by 7, 0.021 moles per liter per second. So because we're making 7 moles of C every time the reaction runs, the overall rate of the reaction is 1/7 of the rate of C production. So how can we compare this to the rate of disappearance of B? Well, again, we can go back to our relationships here. We can either compare C to B using these two relationships, or since we know the rate of the whole reaction, we can then just compare that to B. Alright, so since our rate for the whole reaction is 1/2 change in B, and we know the rate is 0.021, we can then multiply by 2. So the rate of B disappearance is 0.042 moles per liter per second. If we want to use the relationship with C, we can do that as well. So 1/2 change in B over time is equal to 1/7 change in C over time. Since we know information about C, we can fill that in. We would take 1/7 of 0.15 and then multiply by 2, which gets us our same relationship that we had before, 0.042 moles per liter per second. Alright, the next thing we want to look at is finding the rate constant K from a reaction. In the previous video, we looked at how to find the reaction orders from a table, and we're going to look at that again in a second. But once we have the reaction orders, we can use this information to find K. So if you remember from our previous video, NH4 plus was to the first power, NO2 minus is also to the first power, and we can get that information from the table. But how do we find K now? Since K is a rate constant, it should be the same for this reaction regardless of the concentrations we start with. So we just need to pick one of these experiments to fill in our information. And it doesn't really matter which one you pick. So I'm going to pick experiment 8, which is the last one here. So I'm going to put the rate information. 43.3 times 10 to the minus 7 is equal to K times, we're going to use our concentration, 0.2 to the first power times 0.0808 also to the first power. So now it's simply solving for the K value, so we can divide by our 0.2 and our 0.08. So 43.3 times 10 to the minus 7 divided by 0.2 divided by 0.0808 gives us a 0.000268 for our K value. And what are the units of K? So we look at our reaction order. We have first order for each of our reactants, so overall the reaction order is 2. So our units of K are going to be 1 over moles per liter times seconds. And look back at your chart for units of K to make sure you understand this. Alright, once we have our rate law then, our rate law says that rate is equal to 0.000268, 1 over moles per liter per second, times NH4 plus to the first power times NO2 minus to the first power. So this would be our rate law. Now we can fill in any values of our two reactants to get the rate. So what is the rate of the reaction when NH4 plus is 0.3 molar and NO2 minus is 0.09. So we're going to fill in those values. Solving for rate. .3 to the first times 0.09 to the first. Right. So we have 0.000268 times our 0.3 times 0.09. So we have 7.2 times 10 to the minus 6 moles per liter per second. Alright, so let's see if we can do a whole one now. So we want to find reaction orders for our reactants. We want to find our K value so we can write our rate law. So we have NO2 plus CO gives us NO plus CO2. Alright, here's our generic rate law. We need values of K, M, and N here for our exponents. We're going to use the table information to do that. So remember, we're looking for comparing two experiments where our NO2 is changing, but our CO is not changing. Alright, because we want to isolate one variable instead of having to look at both. So I'm going to pick experiments 1 and 2 here and set up my ratio. Now you can do it by looking at what happens to the concentration and what happens to the rate and thinking about our reaction orders, or you can do it mathematically. So I'm going to do the mathematical way of solving it, just so you can see if that might be an easier way for you to think about it. So we're going to set this up in terms of the rate law. So rate law is equal to K times our NO2 to the M times our CO to the N. Alright, so now I'm going to set up a proportion. We're picking experiments 1 and 2. I'm going to use the rate for experiment 2, 0.080 is equal to, don't know K. My NO2 concentration is 0.4, and I don't know M. My CO concentration is 0.1 to the N power. Alright, so this is what I have for experiment 2, filling in our information. Now I'm going to set up the bottom part of our ratio. .0050 is my rate, equal to K times my 0.01 to the M power. So this is my NO2 concentration times 0.10 to the N power. This is my CO2 CO concentration for the first experiment. Alright, so I've set up my proportion here, and since everything is multiplied, I can now cross out things that are on the top and bottom, just like I would with any other expression. So since my CO information is the same, I'm going to cross this out. My K's, whatever those are the same thing, so I'm going to cross those out. Over here, I'm going to divide 0.08 divided by 0.005. So when I do that, I get a value of 16. And then here, 0.4 to the M divided by 0.1 to the M is 4 to the M power. So at this point, hopefully you can see that M has to be 2. And this would be my reaction order. So NO2 is second order. Alright, if this isn't obvious to you, you can set this up as a log ratio. So the log of 16 divided by the log of 4 would be M. And you can put that into your calculator. So we're going to do the same thing for CO. Again, we go back to our table. We want to pick 2 experiments where CO is changing, but NO2 is staying the same. So that's going to be 1 and 3. And we're going to set up the ratio again. So if we look over here at our rates, between 1 and 3 they're the same. So it doesn't matter what you put on the top. I like to put the larger number on top just so I don't get a decimal. But since they're the same, it doesn't matter. So I'll put experiment 1 on the top. So I'm going to fill in NO2, which is 0.1. And at this point I can write the second order if I like, or you can put M, it's not going to matter. And 0.1 for CO, that's to the N because we don't know what that is. And then I'm going to put experiment 2 or experiment 3 on the bottom. So the rate, K value, 0.10 squared for NO2, and 0.20 to the N power for CO. Alright, so we're going to cross out things that are the same. This should be our NO2 information. Our K's are still the same. And in this case, our rates are identical, which is going to give us a ratio of 1 for our rates. Remember, this is 1, not 0. Alright, then our 0.1.2 is going to be 1/2 raised to the n power. So since 1/2 to the n is 1, we know that n has to be 0. And again, if this isn't obvious to you, you can do your log ratios. So log of 1 divided by log of 1/2 is equal to n. Log of 1 is 0, so this is going to always be 0 regardless of what's on the bottom. So this is going to be 0 order. Alright, so now we have our NO2 is second order and our CO is 0 order. So if we write our rate law, rate is equal to some kind of K times NO2 squared. And we can leave off CO because it's 0 order. If you want to put it, you can write CO to the 0 if you wish. But this is just the rate law that we have. So now if we want to identify K, find its value, we can pick any of our 3 experiments. So I'll just pick the first one, fill in our rate information, fill in our NO2 concentration, don't forget your reaction order, your exponent, and then solve for K. .005 divided by 0.1 squared. So K is 0.5. What are the units? So let's look at our overall reaction order. So 2 for NO2, 0 for CO, so overall reaction order is 2. So 1 over molarity times seconds. Alright, the last one we're going to look at on this video uses pictures to tell us the same thing about rate information. Instead of having a table that tells us concentrations and rate values, we have pictures. So these circles represent 4 different experiments where we're altering our 2 reactant values. So we have reactant A, which is the red, and reactant B, which is the blue. So as we change either A or B, we see a change in our rate. So we can use the pictures to find our reaction orders again. So in this one we're trying to find the rate law, so the first step of that is reaction orders. So let's look at our pictures. Alright, so if we look at experiments 1 and 2, we can see we have 2 red and 2 blue. And then in experiment 2, we have 4 red and 2 blue. So the blue is staying constant, the red is doubling. If we look at what happens to the rate then, we also see a doubling. So since the blue is constant, that's not part of our change. Doubling the red doubled the rate. Therefore, we should say that A, or the red, is first order. We see the same effect with concentration and rate. Alright, we want to find reaction order for blue. So let's expand this out. If we look at experiments 1 and 3, the red, or A, is staying the same, 2 red in each. But our blue is doubling from 2 to 4 in experiment 3. And if we look at our rate information, our rate is quadrupled. So doubling B quadrupled the rate. So that should tell us that the B, or the blue, is second order. So we have an exponential effect. So from this we know A is first order, B is second order. So we can write our rate law. We can't calculate K because we don't actually have concentrations, but we can write it as a variable. So A is first order, B is second order. So this would be our rate expression, our rate law expression. So based on this, what should then be the rate of experiment 4? Alright, let's look at experiment 4. So here's our circle. We have 4 reds and 4 blues. So we need to see what happened in order to figure out what the rate is. So if we compare it to experiment 3, experiment 3 we had 2 red and 4 blue. And now with experiment 4, we still have 4 blue, but we're up to 4 red. So B stayed the same, but red doubled. So now we know red is first order. So if the first order red reactant doubled, what should happen to our rate? Okay, remember first order means we see the same effect. So our rate should double. So we started out at 2.0 times 10 to the minus 4. Doubling it should make it 4 times 10 to the minus 4. Alright, so that should be the rate for experiment 4.